Hello, this is Rick Powers from Western Technical College for Introductory Statistics. Working on notes for linear relationships, specifically regression. This lesson is about understanding the input and the output of SALT using linear relationships, specifically for regression. Consider the dataset placebo exercise. We will again use age and systolic blood pressure. Our goal is now about determining a formula for what happens to systolic blood pressure when age changes. The process of finding this formula is called regression. After uploading the data, we choose the variables age and SYST, click on regression, choose age for the explanatory variable, x-axis, and syst for the response variable, the y-axis. Recall the x-axis is horizontal, the y-axis is vertical. Note again, this data is in a cloud, a scattered collection of dots, but we will focus our attention for the moment on the yellow line. What is the information in the yellow line? It is an estimate of the mean for the systolic blood pressure for different values of the age. By doing the hypothesis test, we've proven the positive linear relationship is not just a random chance. In other words, the average systolic blood pressure will increase as age increases. But now we want to know more specifically what that formula is. In SALT, you can see the formula below the graph. Syst is equal to age times 0.7846 plus 100.6648. Sometimes students get confused by this formula, but it's not very difficult to use, really. If I put in a value for age, like age 60, then I would multiply 60 by the 0.7846 and then add 100.6648. The result I get is about 148. What is that telling me? For those people who are age 60, this is predicting that their average systolic blood pressure will be 148. Also, that is a point on the yellow line. If you go over to 60 and then go up to the line, that would be where y is 148. By the way, I think when they did the formula, they should not have used the letter X in between the two things. They should have used an asterisk. That's what computers use for multiplication. Anyway, there are two more things I want to point out about this number, the number 148. First of all, it's not a population mean. All we have here is sample data. So this number 148 is not really accurate. SALT gives us dotted lines here on the graph to show us confidence bands. And you can either see them or not. So the yellow lines are for the confidence interval of the yellow line, which represents the mean. So the yellow line is representing the sample mean, really. And then the confidence bands are saying this would be where the population mean is. If somebody's 60 years old, then the population mean would be between these two dotted lines. Second, after the idea of population versus sample, second, this is not a valid prediction of anyone's blood pressure. It's only a statement of the average. It's only telling what is the middle of the set of data for people who are 60 years old. Now let's take a closer look at the formula. And there's the formula. This can be understood further by considering what algebra tells us about this. One key idea, this is the formula for a straight line. We can use this standard form to understand it. Y is equal to mx plus b. The letter m is the slope of the line. In our case, m is about 0.8. The letter b is the y-intercept of the line. In our case, b is about 101. Hopefully you recall some things about how lines can be explained using slope and intercept. What is the slope? It is the rate of change of y for every unit of x. In our case, for an increase of 1 year of age, the systolic blood pressure will increase by about 0.8. Since this number is positive, the line goes up as x goes up. What is the y-intercept? Many people don't know this. It is the value of y when x is equal to 0. Hopefully it's clear. If I put a value of age of 0 into the formula, all that is left is the intercept. But what does that mean for us? Well, if we took this literally, then newborn babies at age 0 would have an average systolic blood pressure of about 101. However, that's not valid reasoning in this situation. Our data values for x do not go all the way down to 0. Looks like they go down to about 18. In many cases, statistical formulas are not valid for x values which are outside of the data set. The technical phrase for this is extrapolation is not usually valid. Interpolation is valid. That means we can use values within our data set to predict the mean, but we should not use data values that are outside of our data set. One final idea. What is the R squared, which is listed in SALT? You can see it there in the middle. It is a measure of how strong the data relationship is to explain the changes in the y values. In this case, R squared is about 14%. That means about 14% of the changes in a person's systolic blood pressure are explained by their age. So it's not a huge influence, but it does make a difference.